Hi guys. In the last C programming workout, we were implementing a calculator that was using a recursive descent parser, and a user could type in some expressions, actually a sequence of expression statements. And for each expression, the calculator evaluated this expression, printed out the result. So we have a working calculator. Now, how can I motivate the content of the next C programming workout? We were also visualizing the expression trees of these different expressions. We were doing this by kind of messing up our parser. We were inserting this printf functions in the implementation of the parser, so that with a certain indent we could see basically the call stack of these parse functions. And this is kind of not nice to have a code that is not just parsing, but also doing computations and also has this debug information. So one motivation would be now we want to have a cleaner design. We want to have a parser that generates just a tree structure, and afterwards this tree structure can either just be evaluated, but it also could be in addition printed in different ways. For example, printing the tree structure itself. But of course, the actual motivation is that we will use this later for our compiler project, where we actually have to generate tree structures so that after parsing some code, the code generator can generate from these tree structures the assembly code. So basically what we do is we develop now a component that later will be reused in a different way or for a different purpose. And actually I will split this part, this C programming workout part, into 3 videos. In the first video, I will just consider design issues related to this new data structure, which is a bit more complex compared to lists. And I also want to go into a few considerations regarding how to design a good interface for a data structure like that. And then in the second part, I want to focus on algorithms for traversing such trees. And in the last part, I want to in particular show you how we can have a nice representation of this expression tree, so we can use basically in the end LaTeX to get a PDF with actual trees, so that you see things in a way that usually I just show you on the slides. Before I go into the details of this tree structure, I first want to show you in a quick demo how in the end of this workout you will be able to use your calculator to actually generate this PDFs with LaTeX. In the end of this C programming workout, your calculator will no longer just print out the result of an expression, it will print out a LaTeX code like this. And now you can use some shell command magic. You can type in some expression inside of a string for echo. For example, something like that. Pipe it into your calculator and you redirect the output to some file. For example, calc.tech. And then you can use Lua LaTeX for generating a PDF from that. And then of course you can have a look at it. And of course you can use more complicated expressions. Feel free to play around with it once you're done with this workout. Let me just show you one more here. And now let's get started. Of course, the key for representing a complete expression tree is the representation of a single expression node. And here you have to make a first choice. How should you call this structure for a single expression node? The most expressive name certainly would be expression node. But then you also have to consider that in C we do not have function overloading. And if you want to provide functions for accessing expression nodes, then you always have to make this name of the struct kind of part of the function name. So having a long name for this struct would lead to long names for these functions. And then it becomes inconvenient to use these functions. And this typically leads to problems if you have inconvenience in your code. So we need both convenience and expressiveness. And using here just expression is, in my opinion, a good compromise. The next thing is we have to think about what needs to be stored in these expression nodes. We have different kinds of expression nodes. We have some nodes that represent a binary operator. Then we have a node for a binary expression. And in this case, we need 2 pointers to the 2 child nodes. Then we have expression nodes for unary operators. Then we just need 1 pointer to just 1 child node. And then we have these expression nodes that are leaf nodes in the expression tree, where we just have to store a value in the expression node. So before we talk about these members for accessing child nodes or values stored in a node, we first have to think about how to distinguish this different kind of expression nodes. You can distinguish it with the first member, which is some integer, actually some enum type. And for this enum type, we of course will define some enum constants. Of course, you first of all should use meaningful identifiers for this enum constants so that it's already clear from the identifier what kind of expression node you have and what kind of operation this expression node represents. But you also have to make sure that you do not have name conflicts with other enum constants. Here, for example, I avoided that by calling one of these identifiers add and not plus, and similarly sub and not minus, and so on, because otherwise I would have this name conflict with this enum constants from the token kinds. So what you can do is you simply use a prefix for all these enum constants. So here I will use, for example, this prefix ek for expression kind, of course. And maybe we also should use prefixes, by the way, for this enum constants for token kinds, but that's a different story. For this enum constants for expression kinds, it's also a good idea to group them, because you have one group of expression kinds that have 2 child nodes, the binary expression nodes. You have one group of expression nodes that have exactly 1 child node, and you have one group where you do not have any child node at all. And if you group them like here, then you have integer ranges for this enum constants that are not having any gap. And that means you can use a code like this here for making sure that it only gets executed if you have 2 child nodes. Now, sooner or later, however, you will add additional constants because you add additional operators. And that means the name, the identifier for the first enum constant in a group or last enum constant in a group might change. And then you would have to change if statements like this one here all over the place. And that means you have code that is hard to maintain. So what you want to do is you want to use additional enum constants for marking the begin and the end of a group. And the typical design pattern for that is as follows. The marker for the begin of a group has the same value as the first enum constant in this group. And the marker for the end has the value of the last enum constant in this group plus 1. For marking the next group, you don't want to do it like that, because then you would have a gap between these 2 groups. And this would be hard if you have check for whether it's a binary or unary expression node. And to avoid that, to avoid these gaps, you simply use this design pattern that the begin marker for the next group has the value of the end marker of the previous group. And with that, you also, of course, mark the last group for this primary expression nodes. And then it's also simple to check whether you have some valid expression kind at all. So before we continue, let's already begin with writing the header file for this expression type. And first we have to write this include guard for this header file. Of course, we use the typical conventions, name of the project followed by the name of the header file. Then we have this corresponding define and the corresponding endif. And now here we can define this enum constants for this expression kinds. And here I will first define these constants for marking these different groups. So we have this group of binary expressions. we have this group for the unary expressions. And this group for the primary expressions. Okay, and now we can define here this different constants for each group. So this is a group for the binary expressions. And here we begin with add, which has the same value as the begin marker for the binary group. Then we also have sub, we have multiplication, we have division, and we have this power. And then we have this unary group with the unary minus and unary plus. And unary minus is the first in the group, so it gets the value of the begin marker of this group. And the unary plus comes next. And then we have this primary group. We have currently just one primary expression, and that's an unsigned integer literal. And that's the first in this group, so it also gets a defined value. Okay, and for now, that's it. If we have a binary expression, then we need two pointers to these two child nodes, and this will be const pointers, because you will see in the parser, this expression nodes will be generated. It will call a constructor for this expression nodes, and afterwards we actually never have to change this expression nodes, and also not the child nodes of a binary expression. So having const pointers here helps us to make sure that we do not accidentally anyway change this child nodes. We would get an error from the compiler, so the compiler helps us here. Putting them in a struct has the advantage that it's more expressive to access these two pointers. You can access them with binary left and binary right. And here you see the typical use case. You first check whether you have actually a binary expression node, and then you can access these two members. If you have a unary expression, then you just need, of course, one pointer. And of course, you could, by convention, then always use binary left, but then you would have not expressive code. And that's certainly something we do not want, because it sooner or later leads to problems. So we use a different member with a different name, with an expressive name for that. And then the use case, as before, is you first check whether you have a unary expression node, and then you access it like that. If you have a primary expression, then currently this is only the case if we have a literal stored in the node, and then still you see the typical use case. You first check whether you have a expression that just stores a value, and then you can access it here with literal.uint. And again, putting it in a struct means it's more expressive. If you later, for example, have signed integer literals, then you would just add another member here. Okay, and now we can start with declaring constructors and destructors. In the header file for this expression type, we will not provide the complete declaration of this struct. We only provide this incomplete declaration, where we do not show the members of this data structure. So we hide the details. And this makes sure that this data structure only can be used with the functions that we declare in this header file. And these functions will, for example, be the constructors and the destructor, and later some methods for printing an expression tree or evaluating an expression tree. And this makes sure that only those who know about the details and care about the details are actually accessing the internals of this data structure, and that if something goes wrong with manipulating this data structure, this is the place where we should look for bugs. The constructors will allocate memory for a new expression node. That means the constructors also deal with the error handling for allocating memory. And you will actually see there will be one private constructor, a constructor that is only defined and declared in the source file as a static function, which is actually the only place where we call malloc and the only place where we have to do this error handling. Now this first constructor here is for constructing a primary expression for an unsigned literal. It receives, of course, one value that should be stored in this expression node. Then internally, this constructor will allocate memory, initialize this structure, and returns a pointer to that. Then we have another constructor for unary expressions, which first receives an expression kind. And of course, this constructor should check whether this is actually a kind for a unary expression. And it also should check that this second parameter is not the null pointer. It should be a pointer to an already existing child node. And if this check was successful, this constructor will also try to allocate memory, of course, initialize this data structure and returns a pointer. And also the third constructor is basically doing the same for binary expression nodes. Then we also should declare a destructor for releasing memory, because only we know the details of this data structure. That means only we know how to release the memory. So let me first show you how to implement these constructors actually, and write a test program for these constructors, which actually will already call the destructor, but the implementation of the destructor I want to postpone a bit, because the pattern for destructing an expression tree is basically the same as for evaluating an expression tree, and I want to talk about that separately. So this is this incomplete declaration for struct expression, the expression nodes, and after that I will declare all the constructors, and after that the destructor. The constructors always return these pointers to the constructed nodes, and this first constructor receives one parameter for an unsigned integer with 64 bits, and for this type I have to include some header from the standard library for this integer types. And the next constructor is for constructing a unary expression node. It receives first the expression kind, and then a pointer to an expression node that already exists. And then I can just copy that and change it into a constructor for a binary expression node. And this, of course, then gets 2 pointers for the left and right child. And then we also have to declare the destructor, which doesn't return anything and receives a non-const pointer to the root node of the expression tree. It should be non-const because that means that we have the ownership of this tree structure. Now after that we could begin with implementing all these functions, but I actually prefer now to begin with the test program so that I already can check whether I have a correct interface. So that means I will have a program that will not be compiled into an executable because I will get linker errors. But if I only get linker errors, then I know that only the implementations are missing. So in the test program, we just construct a few nodes. Later this will be done by the parser. Some primary expression with some unsigned integer literal, let's say value 2, and then I copy this a few times, and value 2 and value 3 should somehow have different values so that I see differences in the expression tree later. Then we also need some unary expression, some unary minus, for example. And here I will negate value 2. And then some binary expression. So for the sum of val1 and this negated value. So here we have the kind sum and value 1 and neg. And then I just copy this for a second binary expression, which is the product of sum and val 3. Okay, and then I also call the destructor for mal, which will be the root of this expression tree, hopefully. Okay, now let's see that we just get linker errors. No, not the case, so that's why I'm doing this. Now I have a working test program when the implementation of these functions are working. Just linker errors now. Okay, so let's copy this for the implementation of these functions and then begin with the source file of this. Here I just paste this, and then I of course have to include my own header file, and then I have to complete the declaration of this struct. So we first have this expression kind as member, then we have the member for the binary expressions, which is this struct with 2 pointers for the left and right child. So that's the binary member. Then we have the member for the unary expression nodes. And then this struct for the primary expressions. And here we have in the struct just one member. Okay, so this is now the complete declaration, and now I turn this declarations into implementations first, without actually implementing all these functions. I just want to see that I get rid of the linker errors. Here I need a line break actually. No. No, okay. No. This is a definition of a function, and now this also here. So now when I run make again, I should get no more errors, just that warnings that I'm currently not returning anything, which is of course understandable. Now I will make one private constructor, which is just allocating memory. It's not initializing this allocated nodes. But here I can do the error handling, checking whether malloc returned a pointer different from the null pointer and the usual things. So here the usual pattern malloc with size of the dereferenced pointer that we want to have in the end. And then I check whether this is the null pointer, and if this is not the case, then I print this error message and exit with exit code 1. And that of course means that I also have to include a few things. I have to include standard IO and standard lib. Okay, and now we actually can implement all these constructors. They will always do the same. They first allocate memory with this private constructor and get from that a pointer to an allocated node, which is not initialized. And now we initialize the members for the relevant expression kind for this unsigned literals. And that means we initialize the member literal.uint with the value uint. And then we return a pointer to this node. And here, basically the same, but we also have to make sure that this expression kind is actually a valid expression kind. It has to be in this group of unary expression kinds. And we also have to make sure that this pointer to this child node is not the null pointer. So that means we also have to include assert. We only do this in debug mode. Okay, after this check for the preconditions, we now can allocate the memory for this node. And then we initialize this node. The expression kind is what we get as first parameter, and the pointer to the child node is what we get as second parameter. And then we return a pointer. And here we basically do the same. We first check whether this expression kind is an expression kind for a binary expression. And then we also check that these pointers are not null pointers. And then, as above, we first use our private constructor for allocating a memory block for this expression node. And then we initialize it. And again, the expression kind is what we get as first parameter. And then we initialize these two members for the pointers to the left and right child. And then we return a pointer to this expression node. Okay, the destructor I want to show later. Now, okay, some typo. This of course should be exit. Okay, and now this should compile. The next step, of course, would be the implementation of this destructor, but this comes separately. In the next step, we have to think about how to traverse expression trees. You will see that this is already required for implementing the destructor, because we have to make sure that we do not release memory for an expression node before all the memory for all its child nodes was released. Because once you release the memory for an expression node, you lose the access to its child nodes. So this obviously is required. And you will see the algorithm for implementing the destructor basically will be the same as for evaluating an expression tree or printing an expression tree. And this is about traversing expression trees basically.